Hey, it's Horner. We're looking at 1999 M1 for AP Physics C. This is what we call well, it's a pendulum. And what happens is you have a dart that comes in, it hits, sticks to this block, and then pushes it up, and then the pendulum starts to going back and forth. So we actually call this a ballistic pendulum. And you can find out all kinds of things using a ballistic pendulum. So we can look at momentum, relate that to energy, tension in the string, all kinds of really great stuff. So they want us to make sure we answer everything in terms of M, which is the mass of the dart, MO, which is the mass of this block, the maximum angle that you would have between the string and where the string would be uh, angled, and then finally gravity. So the first thing they want us to do is find the speed of the dart immediately before it strikes the block. So we've got to find out what it is. We know from conservation of momentum that little m times the original speed should be equal to the little mass plus the bigger mass, and we can multiply that times the final speed. Notice that there is no term for the big mass in terms of its original speed because it is 0. Let's rearrange this. We're going to end up with V is equal to little m VO over little m plus big M. And that big M, we can always put this O here so that it stays. For the conservation of energy, we're going to say that the original kinetic plus the original potential should be equal to the final kinetic plus the final potential. So they'll put this little prime symbol on there. And we know that that's also equal to 1/2 of the total mass times the speed squared. And that should be equal to the total mass times gravity times height. And it's mainly because we have just kinetic energy at the beginning, so we don't have any potential, and then in the end we just have potential. So that's what you're seeing in terms of the equation here. We know that the height, so the height that it goes from the middle of the block up to the middle of the block can be calculated just by saying the height is equal to, so we notice that we've got this guy right here, okay, so we can find out what what this side of the triangle is. Notice that this and this, okay, so if we have the length of the string which goes down to here, then we have the length of the string that goes down to here. The difference between those two lengths is our height. So our first one would be L, and then all we have to do is subtract off of that L times the cosine of the angle. And it's cosine because this is going to be the adjacent side, and this is going to be our hypotenuse. So anyway, this you can go ahead and make it a little bit easier by factoring out an L. So it's just L is times 1 minus cosine of the angle. And that makes it a little bit easier to see. So now we're going to substitute that in for our height. And so let's go ahead and plug everything in to this equation. So we're going to say 1/2, and then the total mass here is M plus capital MO. And then we know that our speed was this term right here. So it will be M times VO over M plus MO for the larger mass, and then we have to square that. That's equal to the total mass again, so that once again is M plus MO, and we multiply that times gravity, and then our height we said was L times 1 minus the cosine of the angle. At this point now we just need to rearrange this equation for V. There's a lot of algebra to that. I'll let you work through it, and you should end up with this original velocity is equal to little m plus big MO all over little m again times the square root of 2 times g times L times 1 minus, and then here we're going to do the cosine of the angle. And so that's essentially what you need to do for the first part of the problem. You get 5 points for this part of the problem. One of the points that you get is just showing the conservation of momentum. You get another point for the conservation of mechanical energy, so either of the two equations would work. You do get 1 point for finding out what that height is. It's a pretty common thing to see. You get 1 point for plugging everything in, and then you get one more point for rearranging. So if I was taking this test, I would get to this equation and stop because I know that I've got most of the points. I'm only going to miss 1 point, and I'm really focusing on just maximizing the number of points I get. There's a little bit more algebra going from here to here, so that's just kind of why I say that. For letter B, it does say they want have the dart and the block now swing as a pendulum. They want us to determine the tension in the cord when it returns to the lowest point of the swing. So at this point, we know that our net force is going to be equal to MA. So at that point, it would be a centripetal force. So really here, this is AC. Now we could do a free body diagram for this. We know that we've got mg pointing down for both of the objects, so this would really be the total mass. And we know that pointing up is going to be tension. And so what we'll do here is we'll go ahead and plug everything in. The net force is the tension minus m total times g, and that's equal to mass times the centripetal acceleration. Centripetal acceleration, we remember, is v squared over r, but our r here is not really r. In the terms of the problem, it's L. So notice that L here is equal to r. And so from that, what we'll do is we'll go ahead and plug everything in. So now we know that we said that AC is equal to v squared over r, but that's really v squared over L for the problem that we're doing. So now we can plug everything in. T minus the total mass times gravity is equal to the total mass times v squared over L. If we substitute in the m total and the v from what we had before, now we end up with m plus mo times 1 over L times, now we've got mvo over the total mass, m plus mo, and we need to square that, and that should be equal to t minus, and then we have m plus mo times g. So here's that total mass. So we really just flip this. So total mass goes here. We've got L on the bottom, so we're going to just go ahead and put 1 over L because our V from the previous part of the problem is a little bit more complicated. And then we just have T minus, and then here's the total mass times the gravity. So now at this point, we've got to solve for T. So T is equal to now M plus MO times G, and then we're going to have 3 minus 2 times the cosine of the angle. So that is the final thing that you would have in the problem if you substitute and just solve for t. For this problem, parts and what you get for points, you get 1 point for just stating Newton's second law. You get a point for going ahead and plugging in and doing your free body diagram, making sure that you have everything right here. You get 1 point for showing the centripetal force, and then if you substitute everything in, you get this. Really, I think this would be an appropriate answer here. If you want to, you could go ahead and solve it for t and then go ahead and do this, but I don't think that's really necessary. I think as long as you have these 4 points, you're good. Once again, if you don't get this point on the bottom, it's not a big deal. You still have 3 out of the 4, which is a 75%, which in the past has been a 5 on the AP Physics exam for Physics C. Let's go ahead and look at C. At your lab table, you only have the following additional equipment. Without destroying or disassembling anything, design another method for finding the speed of the dart after it leaves the gun. So there are 4 points here. As long as you have some sort of practical procedure that uses some of all or all of the apparatus here, that would work. You can make any assumptions, but you have to recognize those assumptions, and then you have to include any math or any variables that you would use. And so really that's it. You're going to have to think about this one a little bit to find the speed of the dart. You do have a stopwatch. That would be very helpful. You do have a set of known masses, so you could do lots of different things with this. So I'll let you kind of think about what you would do in order to solve that, and we will try that in the lab and see if you can kind of figure out what's going on. The very last part is not on this one, and so we're going to skip the very last part, and that's it.